And sharing the screen. So yesterday, what we talked about was this topic 8 folder, and in particular the new homework with Twitter and Postgres. This is unrelated to the quiz that we were talking about before. That this Twitter Postgres homework is just getting us starting to be familiar with inserting things into the database. The second version of this homework assignment, what this homework is building up to, is inserting things fast, so in parallel. And that will depend on the quiz material. And the next 3 homework assignments that we have in this class are all going to be about combining the Twitter MapReduce stuff that we were doing before with Postgres to make the queries happen in milliseconds instead of hours. I've also posted a topic 9 folder that we might get to today, but probably not. I just put it up here in case that we do, which is going to be going on the actual implementation details of why or how Postgres implements the behavior that happens in the quiz. But today we're really focusing on finishing up the quiz practice problems. And the actual date for this quiz will be a week from today, next Wednesday in class. Reminder for the quiz itself, you will be allowed to use computers. And so in particular, you'll have access to this notes file here. I didn't print out many copies because I assumed most people would prefer electronic ones. It's like 20 some pages long. And you'll also be needing to reference the Postgres documentation, these 3 Postgres pages. And the quiz itself, the practice problems published in the topic 7 transactions. This quiz practice.pdf file right here is the PDF file that we're going over today. And the appropriate Postgres documentation under this references section, these 3 links right here are the things that you'll need to be accessing during the quiz. So that's the problem setup for us. The one thing you will not be allowed to do for the quiz, so you are allowed to use your computer, you are allowed to reference electronic resources and say this PDF file, but you will not be able to actually connect to a Postgres session and type in the commands. So no access to Postgres, just access to the documentation. Before we review what we talked about previously, it's been a long time, so we'll do a lot of review. Before we review the stuff and then start the new material, any questions about the administrative stuff or setup things? Yeah. Next quiz, a week from today, and on this transactions and locks material. Okay, so in each of these problems, again, there are 2 of these sessions listed. Zoom's taken away my ability to zoom. There we go. 2 sessions listed on the left-hand side and the right-hand side. Each of these numbers down here indicates sort of like time. Time is flowing from the top to the bottom, from number 1 to whatever the largest number is. And a command is being run in one of these sessions at a time. And again, you have to be able to predict what all of the statements are doing. So for the select statements, you have to be able to write the actual output of the select statements. All the select statements are very simple. They're just counting the number of rows in the table. But then there's also additional things you'll have to identify, whether the command blocks or whether it has an error or whether it does this thing called deadlocking. The very beginning of this quiz, there were no transactions going on. The transaction uses this begin and commit statement. So when there's no transactions, then any modifications you make to the table are immediately available everywhere else inside of Postgres. And so these select statements over here immediately see the changes over here. Inside of the transaction block, we call the start, begin to commit here. This is a transaction block. These changes are only available after the commit happens here. So line 6, this select statement right here will give us the same exact results as the select statement 2 up here. They both output 0 because even though we've inserted things into the table, it's not yet visible. There's 3 ways to end a transaction block. You can commit the transaction, which saves the results, or you can do a rollback or an abort. If you roll back or abort, those are synonyms of each other. It just means that these changes up here don't take effect. So no matter what you do inside the transaction, if you do rollback or abort, then it's like the transaction never happened at all. The isolation levels only affects how the select statements behave within transaction blocks. Insert statements and modification statements always behave the same way, but select statements will behave differently. The default isolation level, so if we come over here, this is looking at this transaction IO documentation right here. These are the 4 different isolation levels inside of Postgres. The default isolation level is this read committed isolation level. In Postgres, you can do read uncommitted, but read committed and read uncommitted are synonyms of each other. They behave exactly the same way. So if I say read uncommitted, it behaves the same as the default. And in the default level, as soon as the commit happens on the left-hand side, we have access to the changes. So here, even though I'm inside of a transaction on session 2 over here, all these 3 select statements are inside of a transaction. The result of these select statements can change from one line to the next, depending on what has happened inside of other transactions in Postgres. And again, this default, if you have begin by itself, that's the default isolation level of read committed. This repeatable read is the other isolation level that you need to know. And with repeatable read, anytime you have run a command, you're guaranteed to get the same results of that command at other locations in the transaction. So down here with this repeatable read isolation level, this is the syntax for changing the isolation level. The only difference is between these 2 problems is I've changed the isolation level right here. Now all 3 of these select statements are going to get the same results, even though on line 11 over here, it's happening after the commit over here. So with a read committed isolation level, line 11 would give us a 3 value right here because there are 3 things that have been inserted time steps previous to 11. But on the repeatable read isolation level, line 11 here gives us a 0 because we've previously run that command and gotten a 0 from it. Any questions? So this is all review material. It's been a while, so okay, if you've totally forgotten this, but any questions so far about any of this material? Okay, moving on. The more interesting stuff starts happening in this explicit locks section. And in an explicit lock, we're going to, that's what this lock command is doing. And it's confusing because it's hard to hear this difference in English when it's spoken, but a lock is something that you do to a table and it can cause other transactions to block with a B in front of it. And so here on line 3, when I say lock table T in exclusive mode, then this will cause certain other commands not to be able to run. They will have to wait until this transaction over here finishes, until it commits. In order to determine what commands are allowed to run and what commands are not allowed to run, over on, so there's the references again in the topic 7, this 3rd reference down here, this explicit locking is the one that you'll want to use. And We'll click on the table level locks. There's many different lock modes here. But the important thing is this table down here, which tells us which lock modes are compatible with which other lock modes. And the rule is that in order to determine compatibility, is you take the mode that the table is currently locked in. So line 3 right here, it says lock table T in exclusive mode. And so this is the existing lock mode. The existing lock mode is exclusive mode. And then we come down here, it says lock table T in share mode. And in order to know whether we're allowed to do that or not, we look at the requested lock mode down here, find share right here, go across to where it was exclusive. It says X. So if the table is already locked in exclusive mode, you are not allowed to get in a lock in share mode. So because of that, we say that line 5 right here blocks. And a blocking line, I'm asking you to circle the SQL commands that block. So that would be you'd put a circle around this command right here to indicate that this command does not run immediately. It waits until this previous transaction is over, and then it's able to run. Any questions about that so far? Ringing bells, hopefully. Okay, I think this is pretty much where we left off last time. We might have gone a little bit farther in some aspects. I'm going to come over to the this topic 7 notes, and I'm going to scroll down to the bottom where there's a good debugging SQL query that we're going to go over how to use now and how to help us understand the quiz based on it. So under here, under this life pro tips, it'll be pro tip number 3. These first ones, so wrap all of your SQL scripts in transactions. We saw that in the homework assignment we talked about on Monday, that all of the inserting SQL scripts are contained within the begin and commit statements, so that if there's an error anywhere, the whole thing fails. You never have partially created databases. Again, the main purpose of transactions is to protect you from like accidentally deleting things. If you do a delete outside of a transaction, there's no way to undo it. So it's always a good habit to do deletes and updates inside of transactions. This third spot right here, this third bullet point is what we're going to take a look at next. These two queries right here, and we're going to see how we can use these to help us better understand what's going on in the database with these quiz problems. Again, you're not going to be able to run these commands on the quiz, but you can use them to understand why the particular problem is behaving the way it is. So in order to take a look at these, I'm going to come over to a very complicated looking set of windows right here. I'm going to have 3 terminal sessions open here and one this same PDF file open up here. And all of these terminal sessions are in my SQL quiz folder. And so they're all, if I run Docker PS, there we go. I have my SQL quiz database running. Again, each one of these boxes, each one of these problems is like it's on a brand new database system. So it's like we bring the database down and up between each one, and that will delete all the tables and give you a fresh thing to start with. And so the Docker Compose exec pg psql is what I'm using to connect here. And I'll run that in all of them. I have my font size a little bit small, a lot smaller here so that things fit on the screen. Is this, I see heads nodding. Happy to increase the font size if it's helpful. But I think it might be helpful just to be able to fit more things on the screen here. This is the font size that I normally use when I'm working. And I'm going to go through this problem 4 right here. And actually, sorry, that's skipping ahead a little bit. Yeah, let's do this problem 10 that we just talked about. I'll run through that here, and then we'll go on to the deadlocks part. So this explicit locks all these problems. Create table T a int like this. Create table T. Maybe I'll bump this up one more font size. And so that's line 1 that we ran. Then line 2 is the begin here. Line 3, lock table T in exclusive mode. This session 1 is corresponding to my top left terminal up here. And then session 2 will be in my bottom left terminal over here. I will use this session 3 over here for like debugging commands that are not related to these actual sessions up here. So I've just run these 3 commands corresponding to line 1, 2, and 3 in problem 10, and line 4 starting a transaction on the second terminal down here, and then lock table T in share mode. We said that this command right here is going to block because the exclusive mode is not compatible with the share mode, and you know something's blocked in Postgres and pSQL because you type it in, you hit enter, and it doesn't give you back the prompt. It doesn't do yet what it's supposed to do. It's just waiting to know what's going to happen up here before it runs down here. In order to release a lock in Postgres, the only way to release a lock in Postgres is to end your transaction. So that means either committing it or rolling it back. In this case, all we have in this transaction is a lock. So it's the same exact results whether I commit or roll back. There's no insert statements to undo here. And as soon as I press commit right here, then down here, you can see that the lock table is currently goes from the blocked state to a running state, and line 5 here actually gets run after line 6 over here gets run. And then line 7 over here is the commit. So the only thing to do again on this problem is circling line 5 on session 2 because that's the statement that blocks. And again, we knew that it blocked because down here, when I ran this command, it said, didn't say anything, it just stopped and didn't let me do anything until this commit happened up here. Any questions about that? Okay. Maybe one last thing is how this is going to tie into your assignments. For this first Twitter Postgres assignment, this is not going to impact, these locks and blocks are not going to impact things at all. But for your second assignment, where things are happening in parallel, where you're trying to insert, you'll have many Python programs running at once, inserting into the database. That's where the locks and the blocks will come in, and you'll really have to understand this material before completing the second Twitter Postgres assignment. Okay, so that's the explicit locks up here. And on to the deadlocks. So there's new material that we haven't covered yet. For a deadlock, what's going to happen is, this is sort of like the worst case scenario of what can happen with a lock. And I'm going to walk through problem 15 right here, step by step. We'll see what's going on. And then, so we're walking through problem 15 right now. The line 1 up here is creating the table T a int. This is the same exact line that I ran up here before. I could bring the whole database down and bring it back up. That's sort of like the most correct thing to do between problems. But in this case, I'm confident that problem 10 didn't really change the database in any way. The only thing that we've done to the database is create a table. So it's basically just like we've ran line 1 up here and done nothing else. Then, so I'm not going to bring the database down and up, and I'm just going to go on to line 2 right here and create this table U. Create table U, a int, like that. So we have 2 tables. Deadlocks, you don't need to have 2 tables for deadlocks, but it's the most common situation where deadlocks arise is where you have two different tables. Line 3 over here, so now we're beginning a transaction on my session 1, and then lock table T in exclusive mode, lock table T in exclusive mode. And exclusive mode, it's called that way because it's not compatible with anything else. So this is essentially the strongest lock level in Postgres, and so nothing else is compatible with it. Down here, we've run line 4, line 5, begin here, and lock table U in exclusive mode. The important thing here is that this is on a totally separate table right here. This is on table U happening. This lock is happening on table U in line 6, whereas previously on line 4, that was happening on table T. So even though they're both exclusive mode locks, it's separate tables, and so they don't conflict with each other. It's totally allowed to happen. The locks happen at a relational level and not on an entire database level. And that's because I'm saying lock the table and not lock the database. So no locks, no blocks happening up to line 6. Line 7, though, is a different story. Line 7 is happening in session 1 over here. Line 7 says lock table U in exclusive mode. So here, this is blocking our session over here. We can't type anything else in because on line 6 over here, we locked table U, and exclusive mode and exclusive mode not compatible with each other. So that's why we're blocking over here. You would need to circle line 7 right here. Line 8 is in session 2, so lock table T in exclusive mode. And here, what's going to happen is this is also going to block that this line 8 can't happen because line 4 has locked table T in exclusive mode. So if I hit enter, then this command will block. Session 2 is waiting on session 1 to finish, and session 1 is waiting on session 2 to finish. They're both waiting on each other to finish. And so it's impossible for any session to make progress because they're both waiting on each other. So this is what's called a deadlock. When you have a situation where neither session can make progress, then you have a deadlock. I'm going to hit enter right here on this. So I've typed in line 8 right here, but I haven't actually entered it yet. We're going to see what happens in Postgres when you enter a deadlock state. So I hit enter, and for a second there, you could see that it was waiting on both of the transactions. But then you get an error message down here saying deadlock detected. Postgres has a built-in deadlock detector. And anytime it detects a deadlock, it will the actual transaction, the actual command that caused that deadlock will generate an error. By generating an error right here, it ends the transaction on the right-hand side, removing the lock on line 7 right here, the lock on table U. So that allows transaction 1 to make progress, and so that's why Postgres ends the deadlock that way. It turns out that it's actually theoretically impossible to automatically detect all possible deadlocks. That's one of the fundamental theorems of computer science. Theoretical computer science is that you can't automatically detect all deadlock situations. But in this case, it's a very simple deadlock situation. Most deadlocks that happen in practice are simple ones. And so Postgres built-in deadlock detector is able to detect this one and stop it. So for the purposes of the quiz, what you have to do when a deadlock happens, scrolling up here to the top, if a command causes a deadlock, just write deadlock and then stop the problem. You don't have to do any other commands. So this is problem 15 right here. We said we actually do this. We circled this 7 command right here because this blocked because it was accessing table U, trying to lock table U, which had a lock from line 6. But then line 8 right here has a deadlock. And so you just write deadlock. and there's nothing else that you have to do for this problem. In this case, there's no other commands following this problem, but if there were other commands, then you just stop and you don't have to execute them. If the program deadlocks in any way, just all you have to do is write deadlock and nothing else matters. Any questions? Yes.
So after getting the error message, did it essentially like undo line 7 and 8?
So yeah, the question is, so it got the error message, and what exactly did it do? So here we're in the it basically ends the transaction that's going on when it detects the deadlock. It ends the transaction, aborts the transaction, and by aborting the transaction, that removes all of the locks, and that's what allows line 7 to make progress over here. So you're right that it undoes these things up here because it undoes the transaction.
If you have like insert statements, it would pull back those changes.
Exactly. So if you had insert statements and other changes, then it would also roll back those changes. Yeah.
If you had like one table and say on the first session, locked in the second session, locked in like it was locked in that second session, and then like your first session is like not locked in, and then try to lock in that session again.
So with what we have right here, there's no way using the lock table T command with just a single table, there's no way to cause a deadlock. We will see later on how to cause a deadlock with just a single table, but using this explicit lock syntax, there's no way to cause a deadlock.
Should you change the lock status? Like the same session?
So lock table T in exclusive mode. This lock statement, the locking is at a transaction level, so it locks it for the transaction. And you're always allowed to acquire a lock that is the same lock as one you have, or like less than the one you have for your current transaction. You may or may not be allowed to acquire a greater lock. But the lock a lock command like this will never block because of a previous lock command in your current transaction. It's only on an inter-transaction level. Good questions. Any other questions so far? Yeah.
Do like begin, like where you put the begin command or like isolation levels, do those affect the locking at all?
Isolation levels have no effects on locks. Where you put the begin can change whether you have a deadlock or not a deadlock. So if we come as a sort of trivial example of that, basically all these problems in this section right here are just adjusting where the locations of things are. If we have the begin and the commit on the left-hand side happening totally before the begin and the commit on the right-hand side, then we're not going to have a deadlock, because on line 6 right here, when we end this transaction, we're giving up all these locks on both the table T and the table U right here, and so it's not going to conflict. So you have to pay attention on this type of problem to the location, relative location of all of these begin, commits, and lock lines, and also the actual like mode that they're being locked in, that all of those things work together to make the deadlock happen or not happen. Did that answer your question? Any other questions? Okay, so in some sense, at this point, like we've covered everything for the quiz material, and the stuff that is below this is just like more detailed examples and more practical-ish sort of applications. And the main thing that it's testing is going to be implicitly locking things instead of explicitly locking things. So I think, talked a little bit about the implicit locks where, so line 3, we're looking at problem 21 right now. Line 3, this is an explicit lock because we're using the lock command. But every command inside of Postgres does an implicit lock on the table that it is looking at. And so on line 5 right here, let me forget if I've done this before in pSQL, but if you do \bang, this lets you type in a shell command. I want to reset my terminal, so I'll do \bang reset on both of these to clear the screen. And now, so we still have the table T here. Let's do a begin. Oh, there's already a transaction in progress. Let's abort that. Begin. And so now we're on line 3, lock table T in access exclusive mode. And then in order to figure out whether line 4 over here is going to block or not block, we need to know what is the implicit lock level that line 4 is going to acquire. In order to do that, coming back over to our documentation, this is the locking tables, explicit locking.html documentation. You have to do a search. Well, let's see, where it's located is every one of the lock modes in these paragraphs up here has 2 sections. The first one tells you what it conflicts with, and the second section tells you what commands actually cause this lock level to be acquired. The what it conflicts with is the same information that's in the table down here below. This is just much easier to visualize and look at. And so you can ignore this first paragraph, and it's this second paragraph that you'll need to know about for figuring out which lock level the command is acquiring. I'm going to search here for the command that we're looking for, insert. And when I search for insert here, we can see that it acquires the row exclusive lock level. And it tells us right here what things it conflicts with. It tells us that it conflicts with access exclusive right here. Access exclusive is what we acquired up here. So because I'm running an insert command, I know that insert is acquiring the row. The insert command acquires the row exclusive, which conflicts with the access exclusive. And so this command is going to block. So if I type insert into T values 5 like this, I know the command over here is going to block because of what we just looked at. And now we can see that it's blocking. And so the answer to this problem is just circling the 4. This leads us to the helpful debugging statement that I mentioned before at the beginning of the notes. This command right here will tell us exactly what locks are currently outstanding in the database. So this PG locks table is where Postgres stores all the information about locks. And so we can query that table to see what the current locks are for. If I copy that command, and that's what I'll be using this third terminal window for, is to paste in these debugging commands like this, select all of this information from PG locks, and we'll take a look now at exactly what's going on in this table. And this will help us be able to figure out for these implicit locks exactly what the implicit lock is. Is it actually what we predicted it would be, or is it something different? So in this PG locks table, there's a number of different rows inside of here that we'll take a look at. I'm going to, let's see, in order to illustrate exactly what all these rows are referring to, I'm going to stop the problem that we were working on over here. Let's abort both of these transactions, and then do this command at each step of our problem 21 up here. So at the very beginning, when you run the, so there's no transactions going on right here, right now, there's no locks going on. And when you run this select statement, when there's no locks going on, you'll always have these two rows present in your results. There will always be two things locked. And that's because when you run this select statement right here, it's acquiring a lock on PG locks. And so these two rows tell us that there is a lock on PG locks from the select statement that's accessing PG locks itself. The PID over here tells us so that's the process ID of the command that has acquired this lock. We come back over to the documentation over here. There's this select PG backend PID. If I run that, we'll see that gives me a 111. And so that's how I know that it's this terminal over here that has acquired these particular locks on the PG locks table, because the PID is 111. If I run this command right here on the other terminals, then we'll see they have different process IDs, just arbitrarily assigned by the operating system. And so I know it's not these sessions over here that have this lock that's going on. I'll create a lock now. So begin lock table T in access exclusive mode up here. So this is the explicit access exclusive mode lock, line 3 up here in problem 21. And now in my debugging terminal session, I will rerun the debugging query, hit enter. And you can see that on the relation T right here, there is an access exclusive lock. And the PID is 97. That corresponds to this terminal window up here. So I know that it's this terminal window up here that has the access exclusive lock on table T. The granted over here, T, means that it has been granted this lock. It is not blocked. It is not waiting for access to the table. Down here on the bottom left, if I rerun my insert command, insert into T values 5 like this, and then up here, rerun this command right here. So we'll see that we still have the access exclusive lock right here with granted true PID 95. Now we have a new lock right here on the relation T still. Now it's the row exclusive lock, which is what we predicted from the insert statement up here. So this is how we can check to see if our command is giving us the lock level that we expected. We can run this query right here and see that, okay, PID 125, that's this session right here. When I ran the insert command right here, it acquired the row exclusive lock on this particular table. We can also see that it says granted right here is false because it is currently blocked. It is waiting to acquire the lock. It is waiting to be able to do this insert and has not yet been able to do that. Any questions about that? Yeah, I think so from this point on, most of the problems are using these implicit locks. And so this table or this command right here is the good way to make sure that you're understanding exactly what the lock levels are, because you can't just read it off from the problems. Yes.
So like the different exclusive locks here are each in different, like query.
These things?
Yeah. So each of them are cost values and different transactions.
Yeah. So yeah, it might have been more clear if I had added a where relation is not null. Since these ones up here are where the relation is null, they're very technical details about what's going on here. It's locking something other than a table. It's locking the transaction. So you have problem or session 97 has an exclusive lock on its own transaction. And there's other columns that explain that. And so it's down a rabbit hole that we're not going into. Yeah, good question though. Did that answer your question?
Yeah.
Any other questions? Okay, so that's this implicit locks 1. The implicit locks 2 gets into like more interesting commands, a lot of ones that we haven't talked about yet, but we will be talking about later on, about creating indexes, vacuuming, and so on. So my expectation is not that you know what all of these commands do, but that you're at least able to figure out what the appropriate lock level is and whether it's going to block or deadlock or not do any of those things. Next, we're going into these row level locks. And row level locks are things that you cannot do explicitly, you can only do implicitly. And we'll do an example here to see exactly what's going on. So here we're looking at problem 33 right now. And problem 33 still has the create table T, so there's no need to recreate that table, no need to rerun line 1, but we'll do insert into T values 1, and then 2, and then 3 like this. So there's 3 things in our table T. Session 2 down here will begin a transaction, then begin up here. So we've just done line 5 and 6. And now line 7 is where the first interesting thing happens here, where we say update T set A equals 6, where A equals 1. And now line 8 over here, if we say the update T set A equals 7, where A equals, let's see, so this says where A equals 1. I'm going to start us off with where A equals 2 like this and hit enter. And you see that if I do that, there is no blocking action that goes on. If we look at the if we look at the implicit locks caused by the update commands, we'll say that they both get the row access exclusive lock, and there is no conflict on the table level here. So both of those commands can run. I'll abort this transaction so it has no effect. Begin my new transaction. And now let's rerun line 8 right here. Update T set A equals 7, where A equals 1. And now if I hit enter, you'll see that it is blocking right here. So the update command here, depending on my condition over here, sometimes it will block and sometimes it will not block. And in this case, the reason it's blocking is because we don't yet know whether like which rows can have a value equal to 1 and which rows can't have a value equal to 1. Here on line 7, this update command right here, if I were to run the commit command right now, then this action would happen. This row right here would be set equal to 6, and then nothing would match this condition right here, and we would not update anything. But if I were to abort this transaction, then down here, there will be a row that matches A equal to 1. And so we will do an update. So whether something matches this condition over here depends on whether this line right here is aborted or committed. In this particular problem, it says that we're going to commit. So we'll do a commit like that. And then when I do the commit, the line right here is no longer equal to 1, it's equal to 6. And so down here, this says update 0 because this condition does not match anything anymore. Select star from T, and you see that we have the 6 down here instead of the 1. The questions? Yes, question. Yeah, where did the 5s come from? I think previously I ran some insert 5s from the previous problem. Yeah, so it's not from this. So maybe, yeah, if I had been doing the more correct thing of shutting down the database and restarting it, then those wouldn't be there. And so exactly, circle the 8 right here.
It also says that we have to do something whenever an error occurs. Errors
We haven't seen any errors yet. Those will come later.
about
Basically, the errors, so we're going to introduce unique constraints here soon, and the errors will be when you violate the unique constraints.
what if you like roll back, or like try to roll back a transaction? doesn't exist. And that can be set up. Or is it-
So I guess technically, if over here in session 2, without having a begin, I had a commit or a rollback, it would give an error, but I'm not going to do that in problems. Yeah. Okay, we're going to redo this problem now, and we're going to take a look down here at the locks and what's going on at the table level. So I'll go ahead and drop table T. So we get a fresh table to abort this transaction. There we go. Both of them are clear. Let's create table T, a int like this, and insert into T values 1, 2, and 3, and then begin and begin. So we're redoing problem 33 right here. Everything's the same so far up to line 6. We just have 2 transactions running. And over here in my debugging table, if I do select star from T, then we just get the 1, 2, 3 from the inserts up here. And what I want to do is I want to take a look at how these different transactions and commits and everything are affecting my debugging information about the tables and what mode they're locked in. So here on line 7, that's my next line to run, update T, set A equals 6, where A equals 1, like that. Rerun this, and we can see that we get the row exclusive lock on table T from this line right here. Unfortunately, there's no way in the PG locks table to access or to figure out exactly which row has been locked. That it's only this row 2 right here, the row that has a 1 inside of it that's locked, and rows 3 and 4 are not locked. Over here on line 8, if we were to change this A value from A equaled 1 to something else to like 2 and 3, then it would not block anymore because it's only the 2 up here that got locked. So anytime you see that it's like a row exclusive lock, or under PG locks, it says something about rows, there's no easy way to figure out what the row is. Next week, when we're done with this quiz, we'll be talking about how Postgres actually implements these transactions under the hood. And at that point, we'll see ways to figure this out, but requires tools that we don't have yet. So you just have to sort of look at things. So down here, I will do the update T set A equals 7, where A equals 1 command. This command is blocking, and I run this. I guess I've modified my, it would be possible on the blocked command over here to get the information about the actual row level lock. We'd have to look at the PG locks table in detail to do that. But I forgot that the command I gave us here doesn't have that information in the tables it's selecting. So yeah, the takeaway is that you can get the table level locks, but you can't figure out actually which rows are locked, or you can't easily figure out which rows are locked. And you have to just look at the information or look at the problem to figure that out. Everything else in this implicit locks 3, the row level locks, is just following the same patterns. You can get yourself into deadlock situations with just a single table and these update statements by having updates that sort of circularly depend on each other. And so you need to be careful about that when looking at those problems. Any questions about the row level implicit locks? Okay, the unique constraints. So abort, drop table T. The unique constraints is where we can get into error situations. So if we have something like create table T, a int unique like this. Now, the error that could happen, insert into T values 5. And then if I did another insert into T values, actually, we'll do it down here, insert into T values 5 like this. At this point, this is blocking because we don't know whether we're allowed to insert into the table or not, because if we abort up here, then this happens just fine. But if I were to have committed up here, begin, insert into T values 6, and then down here, insert into T values 6 and commit, then we get the error, the duplicate key violates the unique constraint. And so this is the type of error message, the only type of error message, these constraint violations that you might get. So this is going back to the question that Nico asked earlier. In this case, this first problem here, the 5 and the 6, they're totally different values from each other. So there's no possible conflict about the unique constraint. So they don't block each other, and there's no error messages. Let's see. If you have null values in a unique constraint, null values never conflict with other null values. So the null values will never block. Unique constraints is a very common way to get into deadlock situations. So make sure that you work through when working through these problems, pay attention to the deadlock situations under the unique constraint section. More row level stuff. So it happens not just with update statements, but also delete statements take place at the row level. And so whether it's an update or a delete, you'll have to be thinking about the row level situation. One of the, let's see. Okay, yes, foreign keys is the next interesting thing for us to talk about here. So I'm just going to bring down the database now and make sure that we're starting from something totally fresh, because there'll be a handful of things going on here. Up and pSQL, pSQL, pSQL. Here on the foreign keys, so anytime we have a foreign key, table U, the B column right here has a foreign key. This references table T of A. You always have to have a unique constraint on the column that is being referenced by a foreign key. If we did not have this unique constraint right here, Postgres would not let us create this foreign key constraint right here. And so if I do create table T, A int unique, and create table U, B int references T of A like this, begin. So I've just run lines 1 through 4 on this problem 53. Before I go on, a quick aside, any of these create table commands, sometimes I'll have them in session 1, sometimes I have them in session 2. It doesn't matter where the create table happens. The only thing where it matters which session you're in is if you're inside of a transaction like this, or your insert and select statements. The create table commands, if you create the table in session 1, it's available in session 2 as well, so it doesn't matter where you create it at. On line 5 right here, if I do the insert into T values 9 like this, that inserts just fine into T. But now on line 6 over here in session 2, insert into U values 9 like this. Whether we're allowed to insert into the U table or not, whether insert into U values 9. Because there's no, so we tried to just run the command right here, insert into U values 9 right here. At this point, the whether 9 exists in the table or not, whether it exists in T or not, depends on whether we commit to the leftmost transaction. line 6 over here, it will never be able to have access to the information over here because of the isolation level. Says that because this is happening before the commit happens, before this commit over here, this is happening before the commit over here. Line 6 can never know that this T is inserted over here. And so it just immediately errors line 6 over here. So the correct, oh dear, what happened? Unique constraints, foreign key constraints. So it's problem 53 that we're looking at. The answer to this would be drawing the X through this command because it errors, because this command can never have access to the knowledge whether this succeeds or not. If I do the commit up here and then try to rerun this command, get out of the transaction, rerun this command, it would be okay after the commit up here, but before the commit, it's not okay and gives us the error message. This is another thing, because it's happening at the row level, there's no easy way to debug like which values are allowed and not allowed here. You just have to sort of think about it using the what you see in the problem. Are there any questions about the foreign keys?
Sorry, why the insert into U values 9 gives an error?
So there's variations on there to look at with the foreign keys. The deferring constraints is a important concept for us. This will be particularly important on your next homework assignment. And so you can definitely expect there'll be things about deferred constraints on the quiz. In order to set up this problem, so I'm going to first, our D table here has a, well, I'll go ahead and drop my tables, start everything from fresh, reset. I'm gonna first do this problem. You'll notice that this problem only has a single session inside of it, not 2 sessions. I'm gonna first do this problem without line 3, not running line 3, and then I'll redo it with running line 3. So create table T, A, int, unique. So this is the only way that we've seen to create unique constraints before. And now if I begin the transaction, insert into T values 8 like this, the first time I insert into the table, it's fine. There's no duplicate 8 value here. The second time I insert into the table though, I get this duplicate key error violates the unique constraint because you can't have 2 8s inside of here because of this unique. This was not what the problem was asking though. This was without line 3. I'll redo what the problem is asking now, drop table T and create table T, A, int, unique. It's misspelled. Create table T, A, int, unique, deferrable, initially deferred. And now begin my transaction, insert into T values 8, and I can once again insert into T without having an error message thrown. So the when you have this deferrable initially deferred statement, what it means is that any constraints that you have, like the unique and the foreign key constraints, it doesn't check them immediately when you do the insert or update or delete commands. Instead, it checks them all at the end as soon as you do the commit. So down here, if I were to do the commit, then it would throw me the error on the commit line and not on the insert line up here. So for this problem, the correct answer would be to cross out 8 because 8 is the line that throws an error. Whereas if we did not have this line right here, if that was taken away, then it would be line 7 that throws the error. The reason for deferring these constraints, so deferrable initially defers, means that it's deferring checking the constraints until the commit time is because sometimes it's in order to get into a new valid database situation, you have to temporarily get out of a valid database. But as long as you go back into a valid database by the end of the commit, then you can make Postgres happy. Question?
Is there a way to like undo like set then so that you can get back to the value state?
So let's see. So if we did select star from T, there's nothing inside of it right now. If I did begin, insert into T values 8, insert into T values 8. I could do something like delete from T where 8 equals 8, and now I'm back in a valid database state. In this case, there's no way to distinguish between these two insert statements and only delete one of them because the contents of the table is exactly the same. But I did get into an invalid state right here and then back to a valid state from this. And so I never got an error like this. There's slightly more interesting examples here in later on in this quiz, but the next programming assignment will have like real interesting examples. Yeah, the more interesting examples come from like the foreign keys, deferrable, initially deferred. So here you can see that line 8 right here, inserting U into values 8 right here. There's been nothing inserted into the T table. The U table depends on the T table, but this is not going to throw an error because this has the deferrable constraint. And by the time we do the commit down here, we will have a valid value in the T table. So this is getting into a more interesting situation where the deferrable initially deferred actually helps you out. Last part of this quiz is this everything at once section, throwing all these different things together and not giving you any hints about which things you have to be on the lookout for. And so you have to be able to read through this, do all of the things, thinking about all the things that we talked about and figure out what's going on. You should expect that, so there'll be 4 problems on the quiz. At least half of those problems, at least 2 of those problems will be just a big mess, giant mess of things like this. Some of the things will behave normally, some of the things not behave normally. And then some of the other problems might just focus on the smaller things, but lots of problems focusing on the big things like this or focusing on everything together. No focus at all. Any questions on anything about the quiz? Okay. We have a few minutes left in class. We're gonna start going over this, where did it go? This topic 9 MVCC topic. And my hope is that this will help reinforce some of the things that, make, I don't know, it integrates well with the things that go along with the quiz, because this is like the detailed implementation of what's going on with the quiz. MVCC stands here for multi-version currency control, and there's many different ways of implementing transactions in SQL databases, but this is the particular one that Postgres uses. There's this textbook right here, all published online, and you will be, for the final exam, responsible for everything in chapters 1, 2, 5, and 6 of this textbook. I'll cover in class sort of the highlights of these things and how they relate to the homeworks and quizzes, but for the final exam, there will be problems that come from things that we did not at all talk about in class. So you have to maybe not necessarily read through the entirety of those chapters, but you have to know how to read through them for when you encounter that material. One fun thing about this textbook, so it's written by a guy in Japan. If you go to the copyright notice, as long as you don't work at Amazon, then you can do whatever you like with this textbook. But if you work at Amazon, you are not allowed to refer to this document for any reason. So the reason for that is Postgres, or at least this author didn't like how Amazon adopted Postgres in its AWS services, and so he added that. Where did I go? Here we go. So again, MVC, we're covering the implementation details. This will talk about why locks are working the way they do. We previously talked a little bit about the row overhead. We're going to talk, we'll see why there's that 23 bytes, exactly what those 23 bytes are doing. We'll also talk about table overhead, and we'll need this information for making the SQL select queries fast. After this topic right here, everything else in this course will be just about how to make select queries fast. But we need to understand the technical details about how information is actually stored in order to make these queries fast. So some highlights from the reading. I'm going to switch over here for a second, and let's think a little bit more about this this T table. If I do \d T like this, this table has only one column. So again, the \d command gives us information about the columns, and it only has one column right here. And so if I do something like select A from T, I can get that. Let's insert something. Insert into T values 10. Select A from T, it gives me this 10 right here. And if I did something like select B from T or B from T, we're going to get an error because that B column doesn't exist. But it turns out there's a bunch of what are called system columns that exist inside of every table. And one of those is the, well, if we come over to the textbook, here is the this header information about the 23 bytes that's stored in that header. And this xmin, xmax are columns that we can actually select. So like xmin from T, xmax from T, and star. Anytime we see an X, this is going to stand for transaction in Postgres. So X stands for transaction. And this information corresponds to the, every transaction will have an ID, the minimum and maximum transaction IDs that are allowed to access this particular row from the database. I'm just looking at the clock right now. We have about 5 minutes left, so I think it's not worth doing more material for today. We'll just pick up here next week. There's not going to be class on Friday. I'll be available in the office hours, or I'll be available in my office. So welcome to stop by if you have questions about things. Yeah, that's it for today, and hope you all have good rest of the week.